Most of the universe's matter does not shine, does not form stars, does not reflect light, and has never been caught directly in a laboratory. Yet galaxies turn as if it is there, clusters hold together as if it is there, and distant light bends as if invisible mass is quietly shaping the space between worlds. This is the strange calm at the heart of dark matter. Science can measure its gravity with confidence, but still cannot name what it is. If this kind of slow, thoughtful journey helps make the universe feel a little clearer, alike a subscription or a share helps calm space science continue creating peaceful science stories like this one. Thank you for spending your time watching. Please leave a comment telling us where you're watching or listening from, what time it is there, and whether this video is keeping you company while resting, studying, or drifting towards sleep. The story now follows the unseen gravity behind the visible universe. Dark matter begins as a simple problem with a difficult implication. In many parts of the universe, gravity appears to be stronger than the visible material can explain. Galaxies rotate as though they contain more mass than their stars. Gas and dust reveal. Galaxy clusters hold together with more gravitational strength than their luminous contents seem able to provide. Light from distant objects bends as it passes through regions where ordinary matter is not enough to account for the bending. These observations do not begin with a desire for something hidden. They begin with measurements of motion, mass, and gravity. The name dark matter describes the missing part of that gravitational account. It does not mean matter that is black, shadowy, or made of darkness. It means matter that does not emit, absorb, or reflect light in the ordinary ways that telescopes detect. It is called dark because it has not been seen directly through electromagnetic radiation. The broad family of light that includes radio waves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays. It is called matter because it behaves as if it has mass, and because that mass affects the movement of other things through gravity. This is the most careful starting point. Dark matter is not a fully identified substance. It is a name for a pattern of gravitational evidence that points toward an unseen component of the universe. The evidence is strong enough that dark matter has become part of the standard scientific picture of cosmology. Yet the actual nature of dark matter remains unknown. That distinction matters. Science is not claiming to have already found the particle or object that makes up dark matter. It is saying that many independent observations become much more coherent if most of the matter in the universe is not ordinary atomic matter. Ordinary matter is made from atoms. Atoms build stars, planets, rocks, oceans, air, ice, living cells, and the gas between stars. Atoms interact with light because they contain electrically charged parts. Electrons and protons respond to electromagnetic forces, and that response allows ordinary matter to shine, cool, heat, scatter light, form chemistry, and produce the signals detected by telescopes. Dark matter, if it is a new kind of particle, appears to avoid most of that behavior. It does not gather into glowing stars. It does not form bright clouds that radiate strongly. It does not seem to collide and slow down in the way ordinary gas does. Its strongest known effect is gravitational. It adds mass to systems, shapes, orbits, bends space, and helps determine how structures grow. In that sense, dark matter is known through consequences rather than through direct appearance. The situation is similar to many earlier moments in science where an unseen cause was inferred from a visible effect. But the comparison should be kept modest. The effect here is not a single odd motion or one isolated measurement. It appears across many scales, from individual galaxies to clusters of galaxies and the large structure of the universe. The definition of dark matter is therefore tied to a broad pattern. It is whatever accounts for the extra gravitational influence that cannot be explained by visible matter, ordinary gas, dust, radiation, known stars, planets, and other familiar objects. This definition is useful because it does not pretend to know more than the evidence allows. It leaves room for different candidates, while still naming the central fact that something is shaping the universe without showing itself in ordinary light. One of the clearest ways to understand the idea is to begin with the difference between mass and brightness. In everyday experience, visible objects often feel like the important ones because they can be seen. In astronomy, brightness can be misleading. A star may shine strongly because nuclear fusion in its core releases energy. A cloud of gas may glow because it is heated by nearby stars. Dust may block or redden light. A black hole may be dark itself but reveal its presence when nearby material heats and radiates before falling inward. Brightness is therefore not the same thing as mass. Something can be massive and faint, or bright and relatively light. Astronomers can estimate visible mass by measuring starlight, gas emission, and other signals, then using physical models to convert those signals into amounts of matter. They can also estimate total mass through gravity by studying how fast objects move, how systems hold together, and how light is deflected by curved space. Dark matter appears in the gap between these two estimates. The visible inventory gives one amount. The gravitational behavior often requires much more. If the universe contained only the matter that shines or blocks light in familiar ways, many galaxies and clusters would not behave as they do. This does not mean every unexplained motion is automatically dark matter. Astronomers must account for measurement error, hidden ordinary matter, distance estimates, stellar populations, gas temperature, and the assumptions built into gravitational models. Over time, however, those checks have not erased the missing mass problem. Instead, the evidence has widened. Dark matter has become less like a patch for one observation and more like a framework that connects many observations at once. It helps explain why galaxies rotate the way they do. It helps explain why clusters contain so much gravitational mass. It helps explain lensing maps where mass appears separated from hot gas in certain cluster collisions. It helps explain how the early universe could grow from small density variations into the cosmic web seen today. A definition that rests on only one clue would be fragile. A definition supported by several independent clues becomes harder to dismiss, even while its deeper identity remains unresolved. The phrase dark matter also carries a built-in warning. It describes what is not seen, not necessarily what the substance is. There may be one dominant kind of dark matter particle, or more than one dark sector with its own forms of interaction. It may be made of particles that were produced in the early universe and still drift through space today. It may involve very light particles, heavy particles, compact objects, or something not yet imagined clearly. Some possibilities have become less likely as experiments and observations have improved. Others remain open because their expected signals are faint or difficult to separate from background noise. What all serious candidates must do is reproduce the gravitational evidence without violating what is already known about the universe. They must fit the behavior of galaxies, the structure of clusters, the pattern of the cosmic microwave background, and the abundance of light elements formed in the early universe. This is why dark matter is not simply an empty label for ignorance. It is constrained ignorance. The unknown part has a shape because the observations limit what it can be. It must have mass. It must be abundant. It must not interact strongly with light. It must behave in a way that allows cosmic structure to form as observed. In the most common models, it is also cold, meaning that its particles moved slowly compared with the speed of light when structures began to form. Cold dark matter is useful because it can gather gravitationally into broad halos, giving galaxies and clusters a hidden mass distribution that ordinary matter then falls into. The word cold in this context does not describe temperature in the everyday sense. It describes motion. Particles moving too quickly in the early universe would smooth out small structures and make it harder for galaxies to form in the observed way. Slow-moving dark matter allows structure to grow from small beginnings. That growth is one of the reasons dark matter is central to modern cosmology. It is not only added to galaxies after they form, it is part of the explanation for how galaxies form at all. In the early universe, ordinary matter was strongly coupled to radiation. Light and charged particles interacted constantly, and that interaction resisted the early collapse of ordinary matter into dense structures. Dark matter, if it did not interact with light in the same way, could begin collecting under gravity earlier. It could form the gravitational wells into which ordinary matter later settled. Stars and galaxies would then arise within a larger unseen framework. This picture does not make dark matter decorative or optional. It makes it one of the major ingredients in the growth of cosmic structure. Yet the same picture also sharpens the problem. If dark matter is so important, why has it not been found directly? The answer begins with the same property that makes it dark. A substance that barely interacts with light and ordinary matter may pass through detectors almost all the time without leaving a trace. A direct detection experiment has to wait for an extremely rare interaction, distinguish it from natural radioactivity and cosmic rays, and confirm that the signal cannot be explained by anything ordinary. That is a difficult task, and the difficulty grows when the mass and interaction strength of the dark matter particle are unknown. The universe gives strong gravitational evidence, but the laboratory must search across a wide range of possibilities. This difference between cosmic certainty and particle uncertainty is at the center of the subject. On large scales, the case for dark matter is organized, repeated, and mathematically powerful. On the small scale of a detector, dark matter remains absent. The result is not a contradiction, but a tension between two kinds of evidence. Gravity points towards something. Particle physics has not yet revealed what that something is. A careful explanation of dark matter has to keep both truths together. It should not make the unknown sound settled, and it should not make the evidence sound weak simply because the particle has not been identified. The universe appears to contain more matter than visible matter can account for. That matter does not behave like the atoms that make stars, planets, and gas. Its presence is inferred through gravity, through structure, and through the way light and motion respond to unseen mass. Dark matter at this opening stage is therefore best understood not as a finished answer, but as the most successful name for a persistent gravitational reality. It marks the boundary between what astronomy can measure with confidence and what physics has not yet been able to isolate. That boundary is where the subject begins, because the invisible weight is not a small correction to the visible universe. It is part of the structure that makes the visible universe possible. Ordinary matter reveals itself through many kinds of contact. It shines when it becomes hot enough, absorbs light at particular wavelengths, reflects light from solid surfaces, blocks light in dusty clouds, and releases radiation as atoms and molecules change their internal energy. These behaviors are not separate accidents. They come from the structure of ordinary matter itself. Atoms contain charged particles, and charged particles respond strongly to electromagnetic forces. Because of that, ordinary matter can exchange energy with light, with heat, and with other ordinary matter in ways that leave visible or measurable traces. A star is not only massive, It is luminous because ordinary matter inside it becomes hot and dense enough for nuclear fusion to release energy. A cloud of hydrogen gas can be detected because its atoms emit or absorb radiation in recognizable patterns. A planet may be dim compared with a star, but it can still reflect starlight, glow faintly in infrared light, or pull on nearby objects. Ordinary matter is often complex because it has many ways to interact. Dark matter appears simpler in the observations, not because it is necessarily simple in its true nature, but because almost all of those ordinary channels are missing. It does not seem to carry electric charge. It does not form atoms with electrons and nuclei. It does not produce chemistry. It does not cool by radiating light in the familiar way. It does not settle easily into compact, bright objects. What it does reliably is gravitate. That difference is the first deep separation between the known material world and the unseen mass inferred around galaxies and clusters. Gravity acts on both ordinary matter and dark matter, but the other forces do not appear to treat them alike. Ordinary matter can collide, heat up, lose energy, and change form. Dark matter, at least in the standard picture, mostly passes through itself and through ordinary matter without much direct resistance. This does not mean it ignores gravity. It means that when dark matter particles cross a galaxy or a cluster, they do not behave like gas molecules in a cloud. Ordinary gas can crash into other gas, compress, create shocks, heat to high temperatures, and then radiate some of that energy away. That radiation allows ordinary matter to cool and sink inward. Cooling is one of the reasons ordinary matter can become concentrated. Gas falls into a gravitational region, collides with itself, loses energy as light, and gradually forms denser structures. Over long periods, those structures can become disks, stars, planets, and the colder material from which more stars later form. Dark matter does not appear to have an efficient version of that cooling process. Without strong electromagnetic interaction, it cannot easily shed energy as light. It can gather under gravity, but it remains spread out in large halos rather than collapsing into thin glowing disks or dense stellar objects. This difference helps explain why galaxies are not simply made of dark matter in the same visible arrangement as stars. The stars and gas of a spiral galaxy often form a flattened disk because ordinary matter has collided, cooled, and settled. The dark matter halo around that galaxy is expected to be broader, more diffuse, and more nearly spherical, because its particles respond to gravity but do not lose energy in the same way. This contrast between cooling matter and non-cooling matter is central to understanding why dark matter can dominate the mass of a galaxy without dominating its light. Ordinary matter becomes organized into luminous structures. Dark matter supplies much of the gravitational background, while remaining difficult to see directly. The word ordinary can be misleading, because ordinary matter is not simple. It includes hot plasma in stars, cold molecular clouds, heavy elements forged by earlier generations of stars, dust grains, icy bodies, rocky planets, and living systems. In cosmology, however, ordinary matter has a more precise meaning. It is baryonic matter, built largely from protons and neutrons, along with electrons. Protons and neutrons belong to a class of particles called baryons, and this is why astronomers often describe familiar matter as baryonic. Baryonic matter leaves traces in many parts of cosmic history. It affects the formation of light elements in the early universe. It interacts with radiation in the early hot plasma. It produces the light from stars and galaxies. It creates the gas seen in radio, optical, ultraviolet, and X-ray observations. Because it interacts in so many ways, its total amount can be estimated by several independent methods. Those methods do not leave enough room for all the missing gravity to be ordinary matter hiding in a faint form. This was an important step in the argument. For a time, it was reasonable to ask whether the missing mass might be cold gas, dim stars, black dwarfs, wandering planets, faint stellar remnants, or other hard-to-see objects made of atoms. Some of these objects certainly exist. The universe contains many things that are faint, cold, distant, or difficult to detect, but they cannot account for the full dark matter problem. If the missing mass were mostly ordinary baryonic material, it would affect early universe chemistry, background radiation, and astrophysical observations in ways that do not match the evidence. It would also tend to interact, cool, absorb, or emit in some detectable pattern. The dark matter required by the larger cosmic picture must therefore be mostly non-baryonic, meaning that it is not made from the protons, neutrons, and electrons that compose ordinary atoms. That conclusion narrows the question. The universe is not simply hiding enough normal matter in dark corners. The evidence points toward a component that belongs outside the familiar inventory of atomic material. Another difference appears in the way ordinary matter responds to pressure. Gas has pressure because its particles move, collide, and transfer momentum. Radiation has pressure because light carries energy and momentum. In stars, pressure can support matter against gravity for long periods. In the early universe, ordinary matter was closely linked to radiation, and that connection shaped how it could begin to clump. Dark matter, in the common cold, dark matter model, was not tied to light in that same strong way. It could begin to gather gravitationally without being pushed around by radiation as much as ordinary charged particles were. This gives dark matter a quiet but important role in cosmic growth. It forms gravitational wells before ordinary matter can fully settle. Later, when the universe cools enough for atoms to form and radiation stops constantly scattering from charged particles, ordinary matter can fall into those wells more effectively. The difference is not just about visibility, it is about timing, motion, and the ability to build structure. Ordinary matter carries the rich physics of light, heat, pressure, and chemistry. Dark matter carries gravitational influence with far fewer visible side effects. This is why the two components produce such different kinds of evidence. Ordinary matter can be mapped through emission lines, absorption features, thermal radiation, dust patterns, and starlight. Dark matter is mapped through its effects on orbits, lensing, and the growth of structure. The same galaxy can therefore have two overlapping descriptions. One description follows the visible disk, the star-forming regions, the gas clouds, and the central concentration of stars. The other follows the larger gravitational field required to explain motions beyond the bright parts. The ordinary matter gives the galaxy much of its appearance. The dark matter gives it much of its mass. This does not make ordinary matter unimportant. Stars, planets, and complex chemistry are made from it. The visible universe is visible because ordinary matter interacts richly with light. But in the mass budget of the cosmos, ordinary matter is not the dominant form of matter. It is the form that becomes bright, structured, chemically diverse, and observationally detailed. Dark matter is the form that remains mostly hidden while influencing the framework in which those visible details develop. That division also explains why direct comparison can be difficult. There is no known sample of dark matter in a laboratory container. There are no dark matter atoms to place under a microscope. No dark matter spectral lines confirmed by observation, and no established dark matter chemistry. Its properties are inferred by removing what ordinary matter can do and asking what remains required by gravity. It must not interact electromagnetically in the familiar way. It must not be mostly ordinary baryonic matter. It must be able to persist across cosmic time. It must gather enough to shape galaxies and clusters, but not cool so efficiently that it forms the same compact structures as gas and stars. These requirements do not reveal the final identity, but they prevent the idea from being vague. Dark matter is different from ordinary matter in specific, testable ways. Some of those tests have already ruled out simple explanations. Others continue to guide experiments that search for rare particle interactions or subtle astronomical signals. The contrast between the two kinds of matter is therefore not a matter of appearance alone. It reaches into the basic rules of how matter exchanges energy, how it responds to light, how it clumps, how it cools, and how it leaves evidence behind. Ordinary matter is known through contact. Dark matter is known through gravity. The next step is to see how that difference first became unavoidable in the measured motions of galaxies, where the visible contents seemed too light for the speeds they carried. The first strong clues did not arrive as an image of something hidden. They came from motion. When astronomers measure a galaxy or a cluster of galaxies, they are not only collecting light, they are also measuring how matter moves inside a gravitational system. The speed of stars, gas, and galaxies can reveal the amount of mass needed to hold that system together. If the visible material is too light, the motions begin to look excessive. Objects appear to move as though they are responding to more gravity than the observed stars and gas can provide. This was the beginning of the dark matter problem in its modern form. It was not a sudden discovery of a new substance, but a growing mismatch between luminous matter and dynamical mass. Dynamical mass means mass inferred from motion. It is calculated from the way objects orbit, scatter, or remain bound inside a larger system. Luminous mass means mass inferred from the light of stars and glowing gas, in a simple expectation. These two estimates should broadly agree after the faint ordinary material is included. Instead, astronomers found systems where the dynamical mass seemed much larger than the luminous mass. One of the earliest important cases came from galaxy clusters, where entire galaxies move around one another inside a shared gravitational field. In the Coma cluster, galaxies were measured moving at speeds that appeared too high for the cluster to remain intact, if its mass came only from visible galaxies. If the visible matter were all that existed, many of those galaxies should have been moving fast enough to escape, yet the cluster remained a cluster. The implication was uncomfortable but clear in shape. Either the mass had been seriously underestimated, or gravity was behaving differently on enormous scales, or some unseen component was helping bind the system together. At the time, the observational tools were limited, and the conclusion did not immediately settle into the standard picture. Measurements of distance, brightness, and galaxy velocities were difficult. The amount of faint matter was uncertain. Still, the basic form of the problem had appeared. Light was giving one answer, motion was giving another. The gap between them would not disappear. As observations improved, the same kind of tension began to emerge in individual galaxies. A galaxy is held together by gravity, and its stars and gas move in response to the mass inside and around it. If most of the mass were concentrated in the bright central regions, then objects farther out should generally move more slowly, much as distant planets in the solar system move more slowly than planets close to the Sun. This comparison is not exact, because a galaxy is not a single central object with nearly empty space around it. Its mass is spread through stars, gas, dust, and a central concentration. But the basic expectation remains useful. Once the visible mass becomes sparse toward the outer regions, orbital speed should decline unless more mass continues to be present. The surprising result was that many galaxies did not show the expected decline. Their outer gas and stars often moved at speeds that remained nearly steady far from the bright centre. The measurement suggested that the visible disk was embedded in a larger distribution of mass. The extra mass did not shine like stars or reveal itself as ordinary gas. but it affected orbital motion. This was not a tiny correction at the edge of measurement. In many galaxies, the inferred unseen mass outweighed the visible material by a large margin. The galaxy, as seen in starlight, was only part of the gravitational system. The motion of its outer regions was tracing a wider halo that the telescope could not see directly. These early galactic clues were powerful because they rested on a simple principle. Gravity links mass and motion. If an object moves in a stable orbit, its speed depends on the mass holding it there. Too little mass, and the orbit cannot remain bound at that speed. In practice, applying this principle to galaxies requires careful modelling, because galaxies have different shapes, inclinations, stellar populations, and gas distributions. Astronomers must estimate how much mass is present in the visible disk, how much light corresponds to a given amount of stellar mass, and how the gas contributes to the total. But these complications did not remove the pattern. Across many spiral galaxies, the outer rotation speeds remained too high for the visible matter alone. The evidence became especially persuasive when radio observations traced neutral hydrogen gas beyond the bright stellar disk. Neutral hydrogen emits radiation at a characteristic radio wavelength, allowing astronomers to follow gas far into the dim outskirts of galaxies. These extended measurements showed that the flat rotation pattern was not confined to the visible edge. It continued into regions where starlight had already thinned. The farther the observations reached, the more the hidden mass problem became a problem of structure, not merely one of missing stars. The unseen components seemed distributed in a broad halo around the galaxy. It was not simply tucked into the luminous disk, nor concentrated only at the centre. It surrounded the visible galaxy and shaped its motion over large distances. This helped separate dark matter from many ordinary possibilities. A collection of faint stars, cold gas clouds, or stellar remnants arranged exactly where needed became harder to support as the full pattern emerged. The mass distribution required by the motions was larger, smoother, and less directly tied to the light than ordinary matter would usually be. The clue was not that galaxies contained hidden objects. Galaxies certainly do contain many objects that are difficult to see. The clue was that the required hidden mass had a different spatial relationship to the visible galaxy. It behaved like an extended gravitational background. That made the problem deeper. It was no longer enough to say that telescopes had missed some dim material. The missing material had to be abundant, widely distributed, and consistently arranged in ways that explain the measured velocities. The same reasoning also changed how galaxies were understood as physical systems. A spiral galaxy could no longer be treated as only a bright disk of stars and gas with a central bulge. The visible part was embedded in something larger. The disk moved within a halo whose mass shaped its rotation, stability, and history. This hidden halo affected how the galaxy formed, how matter fell inward, and how stars could remain in ordered motion over long times. The observation did not identify the dark matter particle, but it changed the meaning of a galaxy. The boundary of the visible light was not the boundary of the gravitational object. That distinction still matters. When an image of a galaxy shows a luminous disk ending gradually into darkness, it is showing where ordinary matter stops being bright enough to dominate the view. It is not showing where the galaxy's mass truly ends. The mass extends farther out, inferred from motion, and later supported by other methods. In this way, the first galactic clues made dark matter both more specific and more puzzling. Specific, because the motions allowed astronomers to estimate how much extra mass was needed and how it might be distributed. Puzzling, because the extra mass refused to appear through the normal signatures of ordinary matter. It didn't glow as gas, shine as stars, or block light as dust in the required amount. It was present gravitationally and absent electromagnetically. That combination became the defining pattern. Motion marked the presence. Light failed to reveal the source. The careful response was not to declare the mystery solved, but to accept that the visible inventory of galaxies was incomplete. The early clues from galaxy motions did not stand alone, and later evidence would strengthen the case through lensing, clusters, and the early universe. Yet the motion evidence remains foundational because it shows the problem in one of its clearest forms. Stars and gas behave as though the gravitational field is larger than the light suggests. The measured speeds require mass. The observed matter does not supply enough. From that mismatch, the idea of dark matter began to move from a possibility into a central part of cosmic explanation. What came next was a more detailed version of the same problem, written in the rotation curves of spiral galaxies, where the outer regions kept moving as though the invisible halo continued well beyond the bright disk. A galactic rotation curve is a compact way of asking how mass is arranged inside a galaxy. It does not begin with the full image of the galaxy, but with a measurement of speed at different distances from the center. For a spiral galaxy, astronomers examine how stars and gas on one side move toward Earth, and how material on the other side moves away, using small shifts in the wavelengths of light or radio emission. This is the Doppler effect, the physical link between motion and a change in observed wavelength. From those shifts, and from the angle at which the galaxy is tilted, the rotation speed can be estimated across the disk. The result is the rotation curve. If the visible matter contained most of the mass, the curve should tell a fairly direct story. Speeds would rise in the inner region, where more and more mass is included with distance, and then, beyond most of the bright matter, the speeds would be expected to fall. The decline would not need to be perfectly smooth. But once the visible disk thins out, there should be less additional mass to hold fast-moving material in orbit. The outer parts should gradually slow. In many observed spiral galaxies, they do not. Instead, the curve rises near the center and then becomes roughly flat. Gas far from the bright inner regions continues to orbit at nearly the same speed as gas closer in. The outer disk behaves as though the enclosed mass keeps increasing even where the light has already faded. That is the specific force of the rotation curve evidence. It does not merely say that some matter is missing. It says that the missing mass must be distributed in a way that keeps adding gravitational influence at large radii. A flat rotation curve means that the galaxy's mass does not end where the bright disk becomes faint. It continues outward in a broad halo. In this sense, the curve turns a visual boundary into a misleading one. The apparent edge of starlight is not the edge of the system that gravity is measuring. The importance of this result grew because it appeared repeatedly. Different galaxies have different masses, sizes, brightnesses, and structures, yet the same general pattern showed up with striking regularity. The outer rotation speed stayed too high. Vera Rubin, Kent Ford, and other astronomers helped make this evidence central by measuring rotation in spiral galaxies with increasing precision. Their work did not invent the missing mass problem, but it gave it a clear galactic form in nearby systems that could be studied one by one. Each rotation curve became a comparison between visible matter and gravitational requirement. The stars and gas supplied part of the mass. The curve required more. That extra mass could be modelled as a dark halo surrounding the galaxy, extending beyond the luminous disk and shaping the motion of material inside it. The halo was not a decorative addition to the model. Without it, the outer rotation curve could not be held flat under standard gravity. In many spiral galaxies, stars dominate the brightness and contribute substantially to the gravitational field near the center. Gas also matters, especially in the outer disk, where neutral hydrogen can extend far beyond the visible spiral arms. But the more distant the measurement goes, the more the dark halo becomes necessary. The visible disk can explain some of the curve, but not the full pattern. This separation between disk and halo is one reason rotation curves became so useful. They allow astronomers to test how much of the motion can be attributed to stars, how much to gas, and how much remains unexplained without dark matter. There is a subtle point here, because the mass of the stars is not measured as directly as their light. Astronomers use a mass-to-light ratio, which estimates how much stellar mass corresponds to a given brightness. That ratio depends on the ages, compositions, and sizes of the stars in a galaxy. Older stellar populations can contain more faint stars and remnants for the same amount of light. Younger populations may shine more strongly for their mass. Because of this, some uncertainty exists in how much mass should be assigned to the stellar disk. But the uncertainty is not large enough to remove the need for the halo in most cases. Even generous estimates of stellar mass cannot usually produce the observed flat curves in the outer regions. Cold gas can add more mass, but it also falls short. Dust can hide some ordinary matter, but not enough, and not in the broad distribution required. The rotation curve therefore becomes a constraint on both amount and placement. It asks not only how much unseen mass there is, but where that mass must be. A dense concentration of hidden matter near the center would not solve the outer problem. The gravitational influence has to remain important far beyond the luminous disk. This is why the idea of a halo is so natural in the dark matter interpretation. A halo can surround the galaxy and keep contributing enclosed mass as radius increases. The curve does not reveal the halo by sight. It reveals it by the speeds that would otherwise be too large. The shape of the curve also helps distinguish dark matter from a simple inventory error. If the missing mass were just uncounted faint stars mixed with the visible disk, the relation between light and motion would be tighter in a straightforward way. But rotation curves often show that the gravitational structure is more extended than the distribution of starlight. The dark component appears less concentrated, less flattened, and less responsive to the cooling processes that organize ordinary matter into disks. This agrees with the broader idea that dark matter does not radiate energy efficiently. It can gather into a gravitational halo, but it does not settle into the same thin plane as gas and stars. The disk is shaped by collisions, cooling, and angular momentum. The halo is shaped mainly by gravity and long-term orbital mixing. Together they form a galaxy whose visible structure is only one part of its mass structure. The rotation curve is therefore not just evidence for extra matter, it is evidence for a different kind of matter, or at least a different gravitational component, with behavior unlike the material that shines. The evidence becomes especially clear in galaxies where ordinary matter is sparse. Low-surface brightness galaxies are dimmer and more diffuse than bright spirals, yet many still show substantial rotation speeds. Dwarf galaxies can make the point even sharper, because some contain relatively few stars but show motions that imply large mass compared with their light. These systems reduce the chance that the missing mass is only a small correction to stellar modelling. They suggest that dark matter can dominate not just the outskirts of large spirals, but much of the gravitational field in smaller and fainter galaxies as well. This matters for the larger theory of structure formation, because dark matter models predict that halos exist across a wide range of sizes. Galaxies are then not isolated collections of stars that later acquire invisible mass. They are visible concentrations of ordinary matter that form within dark matter halos. The rotation curve is one way of reading that arrangement after the galaxy is formed. It shows the present-day consequence of a deeper structure. Still, rotation curves alone do not answer every question. Some details remain difficult. The inner shapes of dark matter halos, the relation between visible disks and halo profiles, and the behavior of small galaxies have all generated long debates. In simulations, dark matter halos may form dense central regions, while some observations seem to prefer shallower central distributions in certain galaxies. Ordinary matter can complicate this picture by driving gas flows, star formation, and feedback from exploding stars, all of which can alter the central gravitational field over time. The interpretation of a rotation curve therefore requires more than placing a dark halo around a disk. It requires understanding how ordinary matter and dark matter have influenced each other throughout the galaxy's history. That complication does not erase the main evidence, it refines it. The broad need for unseen mass remains, while the exact distribution becomes a more detailed scientific problem. A calm view of rotation curves holds both levels together. The outer speeds strongly suggest extended dark matter halos. The fine structure of the curves continues to test how those halos form, how they respond to galaxies, and whether the standard model captures every relevant process. This is why rotation curves remain central. They are direct, repeated, and physically transparent. A star or gas cloud moving around a galaxy is responding to the gravitational field it occupies. When that response stays far from the center, the mass cannot be confined to what shines. The curve draws the hidden part of the galaxy through motion. It shows that the visible disk is embedded in a larger gravitational system, and that the outer regions are not drifting at the edge of influence. They are still moving under the hold of mass that ordinary light has not revealed. From there, the evidence naturally widens beyond single galaxies, because the same missing gravity appears with even greater force in clusters, where galaxies, hot gas, and dark matter share a larger and more demanding gravitational environment. A galaxy cluster is not only a gathering of galaxies, it is a gravitational system so large that the galaxies themselves become only one visible part of a wider mass arrangement. Hundreds or even thousands of galaxies may move within the same shared field, along with enormous quantities of hot gas spread through the space between them. This gas is not cold, dark emptiness. It is thin, highly heated plasma, often reaching temperatures so high that it shines in X-ray light. In many rich clusters, this hot intra-cluster gas contains more ordinary matter than the stars inside the cluster's galaxies. That fact is important because it makes the missing mass problem harder to dismiss. If only the stars were counted, it might seem possible that astronomers had overlooked a large amount of ordinary gas. But X-ray observations revealed that much of that gas can be measured, and even when it is included, the total visible and baryonic matter remains too small. The cluster still behaves as though more mass is present. The galaxies move too quickly. The hot gas stays confined in a gravitational well deeper than the observed ordinary matter can create by itself. The entire system points toward an unseen component that outweighs both the starlight and the glowing plasma. This is where dark matter becomes a cluster-scale necessity, rather than only a galactic correction. In a single spiral galaxy, the evidence comes strongly from rotation. In a cluster, the evidence comes from several related pressures at once: the motion of galaxies, the temperature of the gas, the shape of the cluster, and the way gravity affects passing light. Each method has its own uncertainties, but they converge on the same broad conclusion. A galaxy cluster has more gravitating mass than its ordinary contents reveal. The earliest version of this problem appeared when galaxy speeds inside clusters seemed too high for the visible mass to hold them together. A cluster is not a rigid object. Its galaxies move through it like separate bodies bound by a common gravitational field. If their speeds are measured and their distribution is estimated, the total mass required to keep the cluster from dispersing can be inferred. This use of motion is related to the same reasoning behind rotation curves, but the geometry is different. Instead of gas circling in a disk, whole galaxies trace the depth of the cluster's gravitational potential. The word potential in this context means the shape of the gravitational environment, the way mass creates regions where other objects can remain bound. When galaxy velocities are too large, the potential must be deep. Visible galaxies alone do not make it deep enough. Later observations added the hot gas as another test. The intracluster gas is so hot that its particles move rapidly. Rapidly moving gas has pressure, and if a cluster did not have enough gravity, that gas would not remain confined. Its temperature is therefore a clue to the cluster's total mass. The hotter the gas, the stronger the gravity needed to hold it in place. X-ray telescopes can measure the brightness and spectrum of this gas, helping astronomers estimate both its temperature and its distribution. Once again, the answer points beyond the ordinary matter. The gas is real and massive, but it is not massive enough to explain its own confinement. It sits inside a gravitational structure larger than itself. Dark matter provides the simplest explanation for that structure in the Standard Model. It forms the dominant mass component of the cluster, while the galaxies and gas occupy the deeper field that the dark matter helps create. This does not make the ordinary matter passive. Gas can collide, heat, cool slowly, and respond to energetic events from galaxies and black holes. Galaxies can merge and disturb the cluster environment, but these visible and detectable components remain embedded in a larger unseen mass distribution. The cluster is therefore a useful laboratory because it separates different forms of matter by behavior. Stars are concentrated inside galaxies. Hot gas fills the cluster volume and radiates in X-rays. Dark matter, inferred through gravity, spreads through the cluster on large scales and dominates the total mass. The proportions vary from cluster to cluster, but the basic pattern remains. Most of the mass is not in the form that shines. This conclusion becomes especially valuable because galaxy clusters are among the largest gravitationally bound systems in the universe. They are not small, local exceptions. They form at the high end of cosmic structure, where gravity has gathered matter over vast regions of space. If dark matter is needed there, then the missing mass problem cannot be treated as a peculiarity of spiral galaxy disks. It belongs to the architecture of the universe on much larger scales. Clusters also provide a bridge between local observations and cosmology. Their abundance, growth, and internal structure depend on how matter clumped over time. A universe with dark matter forms clusters differently from a universe made only of ordinary matter, because dark matter can begin gathering gravitationally before ordinary matter fully decouples from radiation. It helps build the scaffolding that later accumulates gas and galaxies. By the time clusters assemble, their dark matter halos have already shaped where ordinary matter falls. The cluster is a later expression of that early gravitational pattern. This is why the evidence from clusters supports more than the statement that some mass is missing now. It supports the idea that unseen mass has guided structure formation for most of cosmic history. Still, clusters are not simple objects. They are often disturbed, merging, or still settling. Some have relatively smooth central regions, while others show signs of recent collision. Their gas can be stirred, shocked, or displaced. Their galaxies can arrive in groups and subclusters. These complications matter because mass estimates depend on assumptions about equilibrium. If a cluster is relaxed, meaning its components have had enough time to settle into a stable relationship, its gas temperature and galaxy motions can give cleaner mass estimates. If it is merging, the same measurements become harder to interpret. But difficulty in detail has not removed the larger need for dark matter. Instead, cluster mergers have provided some of the most striking evidence that the mass is not simply ordinary gas being miscounted. In certain collisions, the hot gas slows because ordinary gas particles interact and create pressure. The galaxies, being widely separated, mostly pass through. The inferred gravitational mass also appears to pass through more like the galaxies than like the gas. This separation is crucial. If most of the mass were ordinary plasma, the strongest gravitational signal should remain with the gas. In merging clusters where the main mass peaks are displaced from the X-ray gas, the evidence points toward a component that does not collide strongly, does not radiate as the gas does, and yet supplies most of the gravity. Dark matter fits that pattern. These systems are not important because they are visually dramatic, but because they turn behavior into evidence. Ordinary matter and dark matter respond differently during collision. Gas feels pressure and drag. Dark matter largely continues under gravity. The offset between them becomes a way to distinguish mass from ordinary baryonic material. This is a stronger argument than simply saying a cluster contains too little visible matter, because it uses the different physical behavior of the components. The cluster does not only weigh too much, its mass is arranged in a way that follows the collisionless component rather than the colliding gas. That arrangement is difficult to explain if all the missing gravity comes from ordinary matter. It also places pressure on alternatives that modify gravity, because any successful alternative must reproduce not only the amount of gravitational effect, but its spatial separation from the hot gas in such systems. The evidence is not beyond all discussion, and individual clusters require careful modelling. But the cluster scale has repeatedly strengthened the dark matter framework by bringing together galaxy motions, gas physics, and gravitational mapping. The result is a more complete picture of the unseen mass. In galaxies, dark matter appears as the halo that keeps outer material moving too fast for the visible disk. In clusters, it appears as the dominant field that holds galaxies and hot plasma inside a deeper structure. The same idea survives the change in scale. Visible matter marks where the system glows. Dark matter marks where most of the gravity resides. That distinction makes clusters one of the most important stages in the dark matter story. They show that the missing mass is not confined to the outskirts of galaxies, nor to the uncertainties of stellar brightness. It operates where ordinary matter can be counted in several ways and still falls short. The hot gas shines, the galaxies move, the light from farther objects bends. All of these effects point toward a mass distribution larger than the visible inventory. The strain in clusters is therefore not a weakness in the evidence. It is a strengthening of the pattern, because the same unseen component is required under conditions very different from those in spiral disks. The next step is to follow the evidence that does not depend on motion alone. By examining how gravity bends light itself and turns invisible mass into a measurable distortion of the background universe. Gravitational lensing changes the dark matter question because it does not depend on stars, gas, or galaxies moving in a way that must be interpreted through their orbits. It begins with light itself. According to general relativity, mass and energy curve space-time, and light follows that curved geometry as it travels. When light from a distant galaxy passes near a massive foreground object, such as a galaxy cluster, its path can be bent before it reaches a telescope. The distant galaxy may appear stretched, brightened, shifted, or even repeated in multiple images. The foreground object is then acting as a gravitational lens. This does not require the foreground mass to shine. Any mass can contribute to the bending, whether it is in stars, gas, black holes, or dark matter. That is why lensing is so important. It gives astronomers a way to measure mass by its effect on background light, not by the light that the mass itself produces. In the study of dark matter, this is a more direct gravitational probe than brightness, and a different kind of evidence from motion. Rotation curves ask how fast gas and stars move inside a galaxy. Cluster velocity measurements ask how quickly galaxies travel inside a larger bound system. Lensing asks how much mass must lie along a line of sight to produce the observed distortion of more distant objects. The method is not simple, because the bending is often small and the true shapes of background galaxies are not known in advance. But across large numbers of galaxies, patterns emerge. If many distant galaxies behind a cluster are slightly stretched in a coordinated way, that pattern reveals the gravitational field of the foreground cluster. From the distortion, astronomers can reconstruct a map of mass. The result is powerful because it can be compared with the maps of ordinary matter. Starlight shows where the galaxies are. X-ray observations show where the hot gas is. Lensing shows where the total gravitating mass is. In many systems, the lensing mass is much larger than the mass seen in ordinary matter. This supports the same conclusion reached from motion, but through a separate path. The universe appears to contain mass that bends light while remaining mostly invisible in electromagnetic radiation. There are two broad forms of gravitational lensing used in this work. Strong lensing occurs when the alignment and mass concentration are large enough to create clear arcs, rings, or multiple images of the same background source. These features can be striking, but their scientific value lies in their geometry. The positions and shapes of the images constrain how mass must be distributed in the lensing object. Weak lensing is subtler. It does not usually create obvious arcs that can be recognized one by one. Instead, it produces tiny changes in the apparent shapes of many background galaxies. Each individual galaxy may have its own irregular form, so a single distortion is difficult to interpret. But when many background galaxies are measured statistically, their small alignments reveal the mass pattern in the foreground. Weak lensing is especially useful for mapping dark matter across large areas of the sky. It can show how mass is distributed in galaxy clusters around individual galaxies and along the larger cosmic web. This ability makes lensing a bridge between local evidence and cosmology. It does not only ask whether one galaxy rotates too fast or one cluster contains too much mass. It can map the broad arrangement of matter that has grown through cosmic time. The lensing signal is still gravitational, but it is not tied to the motion of the matter being weighed. That independence matters because different methods have different uncertainties. If rotation curves, cluster motions, gas temperatures, and lensing maps all point toward unseen mass, the case becomes harder to explain as a single measurement error or a single misunderstood physical process. Lensing also deepens the evidence because it can locate the unseen mass. This becomes especially important in colliding galaxy clusters. In a cluster collision, different components behave differently. Galaxies are separated by such large distances that they often pass through one another with relatively little direct impact. Dark matter, if it interacts only weakly except through gravity, is expected to behave in a similar collisionless way. Hot gas is different. Gas particles interact, create pressure, heat, and slow. During a collision, the gas can lag behind while the galaxies move ahead. Observations of systems such as the Bullet cluster show this separation clearly. X-ray maps trace the hot gas, while lensing maps trace the largest mass concentrations. The strongest lensing signal is not centered on most of the hot gas. It is displaced toward the regions containing the galaxies. This matters because in clusters, the hot gas contains most of the ordinary baryonic mass. If ordinary matter were responsible for most of the gravity, the lensing mass should follow the gas more closely. Instead, the lensing map indicates that most of the mass behaves like a collisionless component. Dark matter naturally explains that arrangement. It passes through the collision with the galaxies while the gas is slowed by pressure. The result is not just missing mass, but separated mass. The mass is where the dark matter should be, not where the largest amount of ordinary matter is found. This is why merging clusters are often described as strong evidence for dark matter. They allow behavior, not only amount, to be tested. A single mass estimate can always raise questions about calibration, assumptions, or hidden material. A spatial offset between total mass and ordinary gas is harder to dismiss. Any alternative explanation has to reproduce the lensing pattern, the gas behavior, the galaxy distribution, and the dynamics of the collision at the same time. That does not mean every detail of every cluster is settled. Cluster collisions are complex events, and reconstructing their history involves uncertainties in viewing angle, collision speed, gas physics, and mass modelling. But the broad lesson remains important. Lensing can show that the dominant mass component is not simply the bright galaxies and not the hot gas. It behaves as though it is a separate, mostly invisible component. The same approach works beyond dramatic mergers. Around ordinary galaxies, weak lensing can reveal extended halos that reach farther than the visible stars. By measuring the slight distortion of background galaxies around many foreground galaxies, astronomers can estimate the average mass profile of dark matter halos. These measurements agree with the idea that galaxies sit inside larger mass distributions. On still larger scales, cosmic shear, a form of weak lensing caused by the large-scale distribution of matter, traces how matter is arranged across the universe. It shows a web of gravitational structure that includes both ordinary and dark matter, with dark matter supplying most of the mass. This is useful because it connects present-day observations to the growth of structure from the early universe. The pattern of weak lensing can be compared with predictions from cosmological models, including the amount of dark matter, the expansion history of the universe, and the way structures grow over time. In this way, lensing turns dark matter from a galactic problem into a measurable part of the entire cosmic mass distribution. The method is still demanding. The shapes of distant galaxies must be measured very precisely. Telescope optics, atmospheric effects for ground-based surveys, detector behavior distance estimates, and the natural alignment of galaxies can all affect the signal. Astronomers must correct for these sources of error with great care. Lensing is not a simple photograph of dark matter. It is a reconstruction based on how background light has been distorted by foreground mass. Yet the reconstruction is valuable because it follows gravity directly. It does not require dark matter to glow, absorb, collide, or decay. It only requires mass to curve space-time. That is exactly the effect dark matter is known to produce. The evidence from lensing therefore has a restrained but significant force. It gives the invisible component a map. It shows that the missing mass is not only inferred from speeds that look too high, it is also inferred from the bending of light across space. In clusters, it accounts for mass beyond the ordinary gas and galaxies. In merging systems, it can separate from the gas. Around galaxies, it traces extended halos. Across wide surveys, it follows the larger web of structure. Each use carries its own uncertainty, but the repeated pattern is coherent. Gravity is acting where visible matter is insufficient. Light from the background universe is being shaped by mass that does not reveal itself as ordinary radiation. The dark matter idea survives because it can explain not only that extra gravity exists, but where that gravity appears. Lensing does not identify the particle. It does not settle whether dark matter is made of one substance or several. It does not remove every tension in the details of galaxy formation or cluster physics. What it does is make the unseen component harder to treat as a bookkeeping error. When space bends the paths of distant light in a way that matches a larger hidden mass distribution, the argument moves beyond missing brightness. The universe is not only moving as though dark matter is present, It is also distorting the images of farther objects as though that mass lies between them and us. From that evidence, the next question expands from where dark matter is to what it has done over cosmic time, especially in shaping the first small irregularities into the galaxies, clusters, and wide structure now observed. The early universe did not begin with galaxies already in place. It began with a hot, dense state, in which matter and radiation were mixed so closely that the visible structures of a later cosmic history had not yet separated from the background. The galaxies, clusters, and long filaments seen today had to grow from small differences in density. Some regions contained slightly more matter than average, while others contained slightly less. These differences were extremely small, but gravity gave them meaning. A region with a little extra mass pulled on its surroundings a little more strongly. Over time, that pull could increase the contrast, drawing more matter inward and turning a tiny irregularity into a larger structure. Without dark matter, this growth would be much harder to explain. Ordinary matter in the early universe was not free to collapse efficiently at first, because it was strongly coupled to radiation. Charged particles scattered light constantly, and the pressure of that radiation resisted the inward pull of gravity. The universe was expanding and cooling, but before neutral atoms formed, ordinary matter and light behaved as a connected plasma. In that condition, density variations in ordinary matter could not simply fall inward and build galaxies early enough. The pressure from radiation kept pushing back. Dark matter, in the standard picture, didn't interact with light in the same strong way. It could feel gravity without being held tightly to the radiation field. This allowed it to begin collecting into broad gravitational wells, while ordinary matter was still delayed. Later, when the universe cooled enough for electrons and nuclei to combine into neutral atoms, light travelled more freely and ordinary matter was no longer locked to radiation in the same way. At that point, gas could begin falling more effectively into the wells already shaped by dark matter. This sequence is central. Dark matter is not only added to galaxies as an explanation for their present motion, it helps create the gravitational environment in which galaxies can form. The evidence for this early role appears in the cosmic microwave background, the faint afterglow from the time when light first travelled freely through space. That radiation still carries the pattern of early density differences. It is not perfectly smooth. It has tiny temperature variations that correspond to regions of slightly different density in the young universe. These variations allow cosmologists to test how much ordinary matter, dark matter, and other components must have been present. The pattern of peaks in the cosmic microwave background is sensitive to the behavior of matter and radiation before atoms formed. Ordinary matter, because it interacted with radiation, left one kind of imprint. Dark matter, because it added gravity without joining the same pressure-supported motion, left another. The observed pattern fits a universe in which dark matter is much more abundant than ordinary matter. This is a different line of evidence from rotation curves or lensing, because it comes from the early universe rather than from mature galaxies and clusters. It shows that the need for dark matter is built into the initial conditions from which later structure grew. Once atoms formed and the universe became transparent, ordinary gas could fall into dark matter wells. The process was slow by human standards but decisive on cosmic timescales. Gas collected where gravity was already slightly stronger. It compressed, cooled through radiation, and eventually formed the first stars. Those stars changed their surroundings by producing heavier elements, releasing radiation, and ending some of their lives in explosions. Later generations of stars formed in more enriched gas. Small galaxies merged into larger ones. Clusters assembled as matter continued to flow along the developing web. Through all of this, dark matter remained the dominant gravitational background. It did not shine, but it guided where ordinary matter gathered. In simulations of cosmic structure, dark matter forms a network of halos and filaments. Ordinary matter falls into this network, heats, cools, and becomes visible where conditions allow stars and galaxies to appear. The result is the cosmic web, a large-scale arrangement in which galaxies are not scattered randomly, but lie along filaments, sheets, and knots surrounding vast underdense regions. The web is one of the strongest signs that structure formed through gravity acting over long periods. Dark matter helps explain why the web has the shape it does. Because it is abundant and not tied strongly to light, it provides the mass needed for gravity to amplify early differences into the structures now observed. A universe made only of ordinary matter would struggle to grow the same pattern from the small fluctuations seen in the cosmic microwave background. There would not be enough time, and the early pressure effects would hold back collapse too strongly. Dark matter changes the timing. It allows structure to start forming before ordinary matter can fully participate, giving later galaxy formation a head start. This does not mean that dark matter alone determines every detail. Ordinary matter has its own complicated behavior. Gas can cool, form disks, fragment into clouds, ignite stars, and be pushed around by stellar winds, supernova explosions, and energy from growing black holes. These processes can reshape the visible parts of galaxies and even alter the central distribution of dark matter in some systems, but they operate inside the larger framework that dark matter makes possible. The relation is not a simple one-way control. Dark matter shapes where ordinary matter goes, while ordinary matter can modify local gravitational conditions once it becomes dense and energetic. This is why galaxy formation is difficult to model. The dark matter provides a relatively clean gravitational skeleton, but the ordinary matter adds cooling, heating, turbulence, star formation, and feedback. The visible galaxy is the result of both components interacting through gravity, even if they do not share the same electromagnetic behavior. The success of dark matter in explaining large-scale structure comes partly from the fact that it gives the universe the right kind of growth. If dark matter were moving too quickly in the early universe, it would wash out small structures before they could form. This is why cosmologists often describe the leading model as cold dark matter. Cold means that the particles move slowly enough for small-scale density variations to survive and grow. Hot, dark matter, made of very fast particles, would smooth the universe too much on smaller scales, and would tend to form large structures before small ones. Observations show a universe where small structures can form early and then merge into larger systems, a pattern better matched by cold dark matter. This does not prove the exact identity of the particle, but it strongly constrains its behavior. Dark matter must allow the observed hierarchy of structure. It must clump enough to seed galaxies, while remaining diffuse enough to form halos rather than bright compact objects. It must fit the cosmic microwave background, the abundance of galaxy clusters, the distribution of galaxies, and the lensing patterns across large surveys. These are demanding requirements. The idea survives not because it is vague, but because the same basic component helps organize many measurements at once. There are still tensions at smaller scales. Some dwarf galaxies appear to have fewer satellite companions than early simple simulations predicted. Some galaxies show central density patterns that are not always as steep as the simplest dark matter. Only models suggest the distribution of small halos, the behavior of galaxies with very low brightness, and the relation between ordinary disks and dark halos continue to be studied closely. These issues do not overturn the large-scale success of dark matter, but they prevent the picture from becoming final. They may point to the importance of ordinary matter feedback, to limits in simulation resolution, to selection effects in observations, or possibly to properties of dark matter that are not captured by the simplest model. The large-scale universe strongly favours dark matter. The small-scale details still test how completely the standard version describes reality. This balance is important for a careful documentary explanation. Dark matter should not be presented as a solved substance, but it should also not be treated as a loose guess. In structure formation, it acts like a necessary gravitational ingredient. It takes the tiny density differences recorded in early light and helps turn them into the uneven universe of galaxies and clusters. It gives ordinary matter places to collect, while ordinary matter gives those places brightness, chemistry, stars, planets, and observational detail. The visible universe grows inside an invisible mass distribution that came first in the sequence of collapse. This is why the question of dark matter reaches beyond the motion of galaxy edges or the mass of clusters. It reaches into the history of how cosmic structure became possible at all. If dark matter were removed from the standard picture, the universe would have to find another way to grow its web from very small beginnings, while still matching the ancient radiation pattern and the structures seen today. That replacement has not yet succeeded across the same range of evidence. For now, dark matter remains the hidden component that connects the early smoothness of the universe with the later complexity of galaxies. And that connection leads naturally to the next problem if it shaped so much. What could it actually be made of? The search for dark matter becomes more difficult once the evidence has already made its main demand. The universe appears to contain an unseen mass component, but gravity does not say what that component is made of. It gives a location, an amount, a behavior on large scales, and a set of limits. It does not provide a particle label. This is why the candidate list has changed over time. A possible dark matter particle must be abundant, stable over cosmic time, and able to gather gravitationally without shining or cooling like ordinary gas. It must have been produced in the early universe in the right amount, or formed through a process that leaves the same cosmic imprint. It must avoid strong interaction with light, yet still supply the gravity needed for galaxies, clusters, lensing, and structure formation. These requirements narrow the field, but they do not point to only one answer. The most familiar class of candidates is the weakly interacting massive particle. The name describes the basic idea. Such a particle would have mass, would not carry ordinary electric charge, and would interact with normal matter only rarely through forces weaker than the electromagnetic force. This possibility became attractive because some theories beyond the known particle model naturally produce particles with roughly the right behavior. In the early universe, weakly interacting massive particles could have been created in large numbers. As the universe expanded and cooled, they would have collided and annihilated with one another until their density dropped. If the interaction strength and mass fell in the right range, the remaining abundance could resemble the dark matter density inferred by cosmology. This connection made the candidate especially compelling because it seemed to link a particle physics idea with a cosmic measurement. Yet the same strength has become a source of pressure. Experiments have searched for signs of these particles scattering inside detectors, appearing through missing energy in colliders, or producing radiation through annihilation in space. So far, no confirmed signal has appeared. That does not eliminate every version of the idea, because the possible mass range and interaction strength are broad, and some models predict signals too faint for current experiments. But the simplest expectations have been squeezed. The candidate remains important, though less open than it once seemed. Another major possibility is the axion, a much lighter and more elusive kind of particle originally proposed for a different reason in particle physics. The axion was introduced to solve a problem involving the strong nuclear force. the force that holds quarks together inside protons and neutrons. In many versions of the idea, axions could be produced in the early universe and remain as a cold, slowly moving population. Even though each axion would be extremely light, an enormous number of them could supply the required mass density. Axions would not behave like ordinary light or gas, but they might convert into photons under the right conditions in a magnetic field. This possibility gives experiments a specific strategy. They can create strong magnetic fields and look for tiny electromagnetic signals that would indicate axion conversion. The difficulty is that the expected signal depends on the axion mass and coupling strength, and those values are not known. Experiments must search across a range of possible frequencies, slowly testing one region after another. The axion is different from the heavy particle picture. It shifts the imagination from rare impacts in a detector to faint field-like behavior spread through space. It also shows how dark matter may be connected to a deeper problem in fundamental physics, rather than invented only to fix astronomy. Still, the axion has not been confirmed. Its strength as a candidate lies in its theoretical motivation and its ability to behave as cold dark matter, not in direct detection already achieved. Sterile neutrinos form a third path. Ordinary neutrinos are known particles, extremely light and able to pass through matter with very little interaction. They are produced in nuclear reactions, particle decays, and the early universe. But ordinary neutrinos move too quickly and are too light to make up the main cold dark matter component. They would smooth out small structures more than observations allow. A sterile neutrino would be a related but more hidden particle, one that does not feel the usual weak force in the same way ordinary neutrinos do. It might interact only through gravity and through a faint mixing with ordinary neutrinos. Depending on its mass and production history, a sterile neutrino could act as warm dark matter, moving faster than cold dark matter but not as fast as ordinary light neutrinos. This could affect the formation of small galaxies and the number of small dark matter halos. Some searchers look for a faint X-ray signal that could come from sterile neutrino decay. Such a signal would be narrow and difficult to distinguish from known astrophysical emission. There have been hints and debates in the past, but no settled detection. Sterile neutrinos are appealing because they extend a known family of particles rather than requiring an entirely unrelated sector. They are constrained because their decay, abundance, and influence on structure must all remain consistent with observations. They occupy a careful middle ground, neither as heavy and collision-like as the classic weakly interacting massive particle, nor as light and wave-like as many axion models. Primordial black holes offer a different kind of candidate because they are not new particles. They would be black holes formed in the early universe, possibly from dense regions collapsing shortly after the hot beginning. If they existed in the right mass ranges and in sufficient numbers, they could contribute to dark matter. This idea is attractive in one sense because black holes are already allowed by general relativity and do not need to shine by themselves. A black hole can be dark unless material falls into it, or unless it is small enough for quantum effects to matter over cosmic time. However, primordial black holes face strong observational limits. If too many existed in certain mass ranges, they would affect stars, distort background light through lensing, disrupt wide stellar systems, alter cosmic radiation backgrounds, or leave other measurable signatures. Many mass ranges have been tightly constrained. Some windows remain debated or narrow, and the discovery of gravitational waves from black hole mergers renewed interest in whether some black holes might have an early universe origin. But primordial black holes have difficulty explaining all dark matter across broad conditions without conflicting with observations. They remain an important possibility to test, especially because they show that dark matter does not have to be a particle in the usual sense. Even so, the leading cosmological picture still often favours a non-baryonic particle-like component because it fits the smooth, widespread, collisionless behaviour inferred across many systems. Other candidates exist beyond these main examples. Some theories propose a hidden sector, a set of particles and forces mostly separate from ordinary matter. In such models, dark matter might have its own interactions that are weak or invisible from the ordinary side. It could be one particle, several particles, or a more complicated population. Some versions allow dark matter to interact with itself slightly, which might help address certain small-scale structure questions while preserving the large-scale success of the standard picture. But self-interaction cannot be too strong, because cluster collisions and halo shapes place limits on how much dark matter can scatter from itself. Other ideas involve ultralight particles whose quantum wave behavior could influence the centers of galaxies, or asymmetric dark matter, where the abundance is set by an imbalance between particles and antiparticles, somewhat like the imbalance that leaves ordinary matter after the early universe. These possibilities are not equal in evidence, but they reveal the range of the problem. Dark matter is not one guess waiting beside the data. It is a set of constrained possibilities, each trying to satisfy the same cosmic requirements from a different physical starting point. The difficulty is that the large-scale evidence gives broad behavior rather than microscopic identity. A galaxy rotation curve does not say whether the particle is heavy or light. A lensing map does not reveal whether the mass is made of axions, sterile neutrinos, or something not yet named. The cosmic microwave background can measure how much dark matter is present, and how it behaved as a broad component, but it does not directly expose the inner nature of the particle. This is why the search must proceed through elimination as well as hope. Candidates become less likely when they fail to appear where they should, when they produce too much heat, too much radiation, too much small-scale smoothing, too many compact objects, or too many collisions. The unknown gradually becomes smaller, but not yet small enough to close. The most careful conclusion is that dark matter has many possible identities, but none has been confirmed. The candidates survive because they solve parts of the problem without breaking the larger evidence. They differ in mass, origin, expected signal, and relation to known physics. Some would leave rare impacts in deep detectors, some would act like faint fields, some might decay slowly, some might already be compact gravitational objects. Each possibility changes what the next experiment should listen for. That is why the identity question remains the center of the subject. The universe has provided the gravitational outline, but not the material answer. The search must now move from what dark matter could be to why. Despite decades of increasingly sensitive instruments, it has not yet been directly caught. Dark matter has remained difficult to detect directly because the same properties that make it a successful explanation on cosmic scales make it nearly silent in the laboratory. It must have mass, because gravity reveals its presence, but it does not appear to interact strongly with light or ordinary matter. If it did, it would shine, absorb, scatter, cool, or leave familiar traces across space. The absence of those traces is part of the reason the dark matter idea exists at all. A direct detection experiment therefore faces a narrow task. It must find a form of matter that is abundant enough to shape galaxies, yet so weakly connected to atoms that it usually passes through Earth without effect. The expected signal, if it exists, is not a bright flash or a steady stream of obvious events. It may be a rare collision between a dark matter particle and the nucleus or electron of an atom inside a detector. The energy transferred could be extremely small. The event could look similar to signals produced by ordinary radioactive decay, cosmic rays, neutrons, detect a noise, or trace contamination in the materials surrounding the experiment. The challenge is not only to build a sensitive instrument, it is to build an instrument that can distinguish an almost silent possibility from a much larger background of ordinary processes. This is why many direct detection experiments are placed deep underground. Rock above the detector helps block cosmic rays, which are high-energy particles arriving from space. Even far below the surface, however, the environment is not perfectly quiet. Natural radioactivity exists in rock, metals, glass, dust, and even in tiny impurities inside the detector itself. Neutrons can be produced by radioactive processes in surrounding materials. Muons from cosmic rays can still reach deep sites, though at much lower rates. Electronics can produce noise, temperature changes, vibrations, and small imperfections in calibration can imitate or obscure weak signals. A dark matter experiment has to reduce all of this as much as possible, then measure what remains with great precision. Some detectors use ultra-pure liquid xenon or argon, waiting for a particle interaction to produce a small flash of light and a small amount of electric charge. Others use crystals cooled to extremely low temperatures, searching for tiny vibrations or heat pulses caused by a particle strike. Some look for interactions with electrons rather than nuclei. Each design is an answer to a different part of the same question. If dark matter occasionally touches ordinary matter, what kind of touch is it? How much energy does it transfer? And how often should it happen? The problem is that the answer could lie across a wide range of masses and interaction strengths. A heavy dark matter particle might strike an atomic nucleus with enough energy to be noticed in one kind of detector. A much lighter particle might transfer too little energy for that detector to see. A particle that interacts through a rare process may require enormous detector mass and long exposure time. A particle that interacts only through a specific coupling may be missed by an experiment built for another signal. This is why a non-detection does not simply mean dark matter is absent. It usually means that a certain kind of dark matter, with a certain range of masses and interaction strengths, has become less likely. Over time, these exclusions are important. They shrink the allowed space of possibilities, but they do not close the whole question unless they cover every plausible form. The dark matter problem is difficult partly because gravity gives strong evidence for a broad component, while direct detection must search through detailed particle possibilities one by one. There is also the problem of certainty. In a detector designed to see rare events, a small excess can be tempting. But science has to ask whether it is stable, repeatable, and free from ordinary explanation. A few unusual events may arise from unknown backgrounds. A seasonal variation may be caused by environmental effects. A signal that appears in one detector but not in others may depend on assumptions about the dark matter particle, or it may reflect an unrecognized source of noise. The expected motion of Earth through the galaxy adds another layer. If dark matter forms a halo around the Milky Way, Earth should move through that halo as the solar system orbits the galactic center. This motion could create a yearly modulation in the detection rate, because Earth's orbital motion around the Sun sometimes adds to the solar system's motion through the halo and sometimes subtracts from it. In principle, such a modulation would be a useful signature. In practice, many ordinary effects also vary with season, including temperature, detector conditions, and environmental backgrounds. A convincing dark matter signal would need to match the expected timing, energy distribution, detector response, and independent confirmation from other experiments. The standard for proof is high, because the claim is high. Detecting dark matter directly would identify a major component of the universe, so a signal cannot rest on ambiguity. It must survive attempts to explain it through known physics. This caution has shaped the field for decades. Some experiments have reported hints, anomalies, or excesses that attracted serious attention. Other experiments, using different materials and methods, have failed to confirm them under the simplest interpretations. The result is not scientific failure in a simple sense. It is the process of narrowing a difficult target. Each null result says that dark matter, if it belongs to the tested class, must be rarer in its interactions, lighter, heavier, or different in character than the experiment was able to reveal. The absence of a signal becomes information, but it is not the same as an answer. It changes the map of the unknown. Indirect detection faces a related but different difficulty. If dark matter particles can annihilate with one another or decay very slowly, they might produce ordinary particles, gamma rays, neutrinos, or antimatter. Astronomers then search places where dark matter should be dense, such as the centers of galaxies, dwarf spheroidal galaxies, or galaxy clusters. The difficulty is that the universe contains many ordinary sources of high-energy radiation, pulsars, supernova remnants, black hole environments, cosmic ray collisions, and energetic gas can all produce signals in the same general range. A possible excess has to be separated from all of these. Dwarf spheroidal galaxies are useful because they contain much dark matter and relatively little ordinary astrophysical activity, but their signals are faint. The galactic center is attractive because it may contain a high dark matter density, but it is crowded with ordinary sources and complex gas. A clean indirect signal would need a pattern in energy, direction, and source class that known astrophysics cannot explain. Once again, the problem is not only sensitivity, it is interpretation. Particle colliders offer another path, but they also face a missing signature problem. If dark matter particles can be produced in high-energy collisions, they may escape the detector without leaving direct traces, carrying away energy and momentum. Physicists then look for an imbalance, where visible particles are measured on one side and missing energy suggests something invisible left the collision. But neutrinos also escape detectors and create missing energy. Measurement errors can imitate imbalance. New particles, if produced, may decay through complicated chains, even if a collider found missing energy beyond known expectations. It would not automatically prove the particle is cosmic dark matter. It would need to match the abundance, stability, and behavior required by astronomy. A collider can reveal a possible invisible particle. Cosmology must still show whether it is the unseen mass-shaping galaxies. This connection between experiments and the sky is one of the central difficulties. Dark matter is a cosmic problem that likely requires a microscopic answer, and the two sides do not meet easily. A direct detector might measure a mass and interaction rate. An indirect search might find a radiation feature. A collider might produce an invisible particle. Lensing and cosmic structure measure gravity over enormous scales. To become a complete discovery, these pieces would need to support the same identity. Until then, each result remains partial. The quiet difficulty of dark matter detection is therefore not caused by lack of effort. It comes from the nature of the target. The particle, field, or object responsible may avoid the ordinary forces that make matter visible. It may have a mass outside the best explored ranges. It may interact through a channel no current detector is optimized to see. It may be part of a dark sector, with behavior more complicated than the simplest models. Or it may require a shift in gravitational theory that still has to reproduce all the evidence usually assigned to dark matter. The unanswered question survives because the universe is clear about the gravitational need and unclear about the physical source. Direct detection tries to turn that gravitational need into a laboratory event, but the event may be rare, faint, and easily hidden among ordinary backgrounds. That is the central constraint. Dark matter is not hard to believe in because the evidence is thin. It is hard to catch because its known effects are gravitational, while the instruments built to identify it must rely on some additional interaction that may be extremely weak. The search continues in the narrow space between absence and proof, where each quieter background and each stronger limit brings the field closer to either a detection or a more precise understanding of what dark matter cannot be. Searching for dark matter is not a single experiment repeated in different rooms. It is a set of approaches aimed at the same hidden component from different sides, because no one yet knows which physical trace, if any, will be the one that ordinary instruments can catch. The underground search begins with the most direct hope. If the Milky Way is surrounded by a dark matter halo, then Earth is moving through that halo, and dark matter should be passing through laboratories at all times. Most of it would cross the planet without interacting. A very small fraction might strike an atomic nucleus or electron, leaving a detectable recoil. This is the principle behind many deep underground detectors. They are placed beneath mountains or deep inside mines not because dark matter needs darkness, but because ordinary cosmic radiation has to be reduced. The detector itself is then built from materials chosen for purity, stability, and predictable response. Liquid xenon and liquid argon experiments use large volumes of noble elements, substances that can produce faint flashes of light and freed electric charge when a particle deposits energy. By comparing these signals, the experiment can estimate where the event occurred and what kind of interaction it may have been. Other detectors use crystals or semiconductors cooled, until even a very small energy deposit can be noticed as heat, charge, or vibration. The quietness of these instruments is active, not passive. Layers of shielding, careful material selection, background modeling, and calibration sources all work together to make an extremely rare event stand out if it occurs. Every improvement has meaning even without discovery, because a cleaner detector can exclude a wider range of dark matter behavior. The underground path is strongest when dark matter behaves like a particle that sometimes scatters from ordinary matter. It is less effective if the particle is too light, too weakly coupled, or connected to ordinary matter in a way the detector is not designed to read. For this reason, direct detection has widened beyond the classic search for heavy particles hitting atomic nuclei. Some experiments now focus on lighter candidates that might interact with electrons or produce smaller energy transfers. Others explore materials where tiny disturbances can be amplified, or where the internal structure of the material gives access to signals that older detectors could not easily see. This expansion matters because the failure to find one kind of dark matter has shifted attention toward less explored possibilities. The search has become less like waiting beside one doorway, and more like testing many possible ways the hidden component could leave a trace. A separate route turns toward axions and axion-like particles. These searches often rely on the possibility that such particles can convert into ordinary photons in a magnetic field, in a resonant cavity. A strong magnet and a carefully tuned detector can search for a faint signal at a particular frequency. If the frequency matches the mass of the axion, a tiny excess of electromagnetic power might appear. The method requires patience because the unknown mass has to be scanned gradually, with the instrument tuned and retuned across possible values. Other axion searches use different arrangements, including magnetic fields in the laboratory, astrophysical environments, or precision measurements that might reveal how axion fields affect known particles. These experiments show that the dark matter search is not limited to impacts. It can also look for conversion, oscillation, or subtle changes in fields. The signal may not be a particle strike at all. It may be a faint rhythm, a narrow line, or a small shift in a well-controlled system. Particle colliders approach the problem from another direction. Instead of waiting for cosmic dark matter to interact naturally, they try to produce new particles in high-energy collisions. At facilities such as the Large Hadron Collider, protons are accelerated and smashed together, creating conditions where heavy or weakly interacting particles might briefly appear. If a dark matter particle were produced and stable, it would likely pass through the detector unseen. The evidence would be indirect, appearing as missing energy and momentum balanced against visible particles created in the same collision. Collider searches are valuable because they can test links between dark matter and known particle physics. They can look for mediator particles, which would be particles that connect dark matter to ordinary matter, or for broader signs of physics beyond the known particle model. But collider evidence would need caution. Producing an invisible particle does not automatically prove it makes up the cosmic dark matter. The particle would have to be stable enough, abundant enough, and consistent with astronomical measurements. A collider could open a door into the dark sector, but cosmology would still have to show whether the discovered particle is the mass that shapes galaxies. Astronomical searches provide yet another path by looking outward rather than underground or inside accelerators. If dark matter particles can annihilate when they meet, or decay over long periods, they might produce ordinary radiation or particles. Telescopes then search for excess gamma rays, X-rays, neutrinos, or antimatter from regions where dark matter should be concentrated. The centers of galaxies, dwarf spheroidal galaxies, galaxy clusters, and the diffuse background radiation all become possible testing grounds. Dwarf spheroidal galaxies are especially useful because they appear to contain large amounts of dark matter and relatively little star formation or gas that would create confusing high-energy signals. The center of the Milky Way may contain more dark matter, but it also contains many ordinary sources, making interpretation harder. Space telescopes, ground-based gamma-ray observatories, neutrino detectors in ice or water, and instruments that measure cosmic ray particles all contribute to this wider search. Their strength is scale. They can examine environments that no laboratory can recreate. Their weakness is complexity. The sky is full of ordinary high-energy processes, and a possible dark matter signal must be separated from pulsars, black holes, supernova remnants, gas collisions, and cosmic ray interactions. The same principle also guides searches for compact dark matter candidates, such as primordial black holes. If dark matter were made of many compact objects, they would not need to emit light, but their gravity could reveal them. Astronomers look for microlensing, a temporary brightening of a background star when a compact object passes in front of it and bends its light. The duration and frequency of such events can limit how many compact objects exist in certain mass ranges. Other observations test whether such objects would disturb stars, affect wide binary systems, contribute to gravitational wave events, or alter background radiation. These searches have ruled out many simple versions of compact object dark matter, though they continue to examine remaining windows. The method is important because it does not assume a new particle. It asks whether gravity alone, acting through unseen compact bodies, could supply the missing mass. So far, the answer appears limited. Compact objects may exist and may contribute in some range, but they do not easily account for all dark matter without conflicting with other observations. Across all of these searches, the most important feature is complementarity. Each method sees only part of the possible landscape. Underground detectors are sensitive to scattering. Axion experiments listen for conversion or field effects. Colliders test production. Telescopes look for decay, annihilation, or compact gravitational signatures. Cosmological surveys measure the distribution of matter and the growth of structure. No single null result can erase the entire dark matter idea. because each experiment depends on assumptions about mass, interaction, abundance, and signal type. But the experiments are not isolated. Together they close regions of possibility. If a particle is not seen in direct detection, collider limits and astronomical searches may test related interactions. If a gamma-ray excess appears, dwarf galaxies and laboratory experiments can check whether it fits a dark matter interpretation. If a new invisible particle appears in a collider, cosmology can test whether it has the right cosmic history. A true discovery would become strongest when several paths begin to point toward the same object. The present situation is quieter. Many searches have reached impressive sensitivity, and many simple models have been constrained. Yet the unknown remains broad enough that the effort continues. This is not a sign that the field lacks direction. It is a sign that dark matter is defined by strong gravitational evidence but weak non-gravitational access. Experiments must therefore surround the problem rather than approach it through one guaranteed channel. Underground instruments reduce noise until a rare recoil might become visible. Magnetic searches scan patiently for an axion signal. Colliders test whether invisible particles can be created from energy. Telescopes study places where dark matter is dense enough that decay or annihilation might matter. Surveys map how mass is arranged across the universe. Each approach asks the same basic question in a different language, whether the unseen mass that shapes cosmic structure also has a small doorway into ordinary physics. Until that doorway is found, the search remains a careful narrowing of possibilities, and the absence of detection becomes part of the evidence that any successful answer must explain. The strength of dark matter does not remove the need to test alternatives. A scientific idea becomes stronger when it survives comparison with other explanations, especially when the evidence is indirect. Dark matter is inferred through gravity, motion, lensing, and structure formation, not through a particle already held in a detector. That leaves room for a serious question. Perhaps the missing mass is not a new substance at all. Perhaps the law of gravity, as currently used across galaxies and clusters, is incomplete. This possibility has been explored for decades, most often through modified gravity, a broad family of ideas that changes the way gravity behaves in certain conditions. The motivation is understandable. In spiral galaxies, the need for dark matter appears where accelerations become extremely small, far weaker than those experienced inside the solar system. If gravity changes in that low acceleration regime, then flat rotation curves might arise without surrounding every galaxy with a large invisible halo. The best-known version of this approach is modified Newtonian dynamics, which proposes that below a very small acceleration scale, the relation between force and motion changes from the familiar Newtonian form. Its appeal comes from a real pattern. Many galaxy rotation curves show a tight connection between the visible matter and the observed acceleration. The stars and gas do not explain the full gravity under standard assumptions, yet they seem closely related to the shape of the rotation curve. This relation is not random, and any successful dark matter model must explain why ordinary matter and inferred dark matter appear so strongly linked in many disk galaxies. Modified gravity approaches take that link as a clue that the law itself may be different. The difficulty is that galaxies are not the only evidence. An explanation that works for spiral rotation curves must also account for galaxy clusters, gravitational lensing, the cosmic microwave background, the abundance and growth of structure, and the behavior of merging clusters. This is where many modified gravity ideas face pressure. Clusters still appear to require extra unseen mass, even when gravity is adjusted. Lensing maps often show mass distributions that do not follow visible matter in the simple way a pure modification would prefer. In colliding clusters, the main lensing mass can separate from the hot gas, which is where most of the ordinary matter resides. A modified gravity theory can try to reproduce this through additional fields or more complex rules, but then it begins to resemble a theory with unseen components of its own. The distinction between modified gravity and dark matter becomes less clean. If a new field is added to make lensing and cosmic structure work, the field may behave partly like an invisible gravitating ingredient. The question then changes from whether anything unseen exists to what kind of unseen physics is being introduced. The standard dark matter picture remains successful because it can connect many scales with one main component. Cold dark matter helps explain galaxy halos, cluster masses, lensing patterns, and the early growth of structure. It is not perfect in every detail, but it does not have to invent a different rule for each system. Its weakness lies elsewhere. It has not yet revealed its particle identity. Modified gravity has the opposite tension in many cases. It can capture some galactic regularities with striking economy, but it struggles to match the full cosmological evidence without added complexity. This difference makes the debate useful rather than merely oppositional. Dark matter models must explain why visible matter and inferred gravitational acceleration are so tightly related in galaxies. Modified gravity models must explain why the universe behaves as though a non-luminous mass component shaped it from early times onward. Each side exposes the unfinished parts of the other. Small-scale tensions also keep the discussion active. In the simplest simulations containing only cold dark matter, halos form with certain expected properties. Some observations of dwarf galaxies and low-brightness galaxies suggest central mass distributions that may be less dense than those simple simulations predict. There have also been questions about the number and behavior of small satellite galaxies around larger galaxies. These issues are sometimes described as small-scale challenges to cold dark matter. They do not erase the strong evidence on large scales, but they show that the path from dark matter particles to real galaxies is not straightforward. Ordinary matter changes the problem. Gas cools, forms stars, is heated by radiation, and can be driven outward by supernova explosions. Energy from young stars and growing black holes can rearrange gas, and because gravity responds to the total mass distribution, repeated gas movement can also alter the inner dark matter profile. A simulation that leaves out these processes may predict a clean halo that real galaxies never preserve. This means that some apparent tensions may come from incomplete modelling of ordinary matter, rather than from failure of dark matter itself. But that answer has to be demonstrated carefully, not assumed. The same feedback processes that solve one problem must not create new ones elsewhere. Galaxy formation is a demanding test because it combines the relatively simple gravity of dark matter with the complicated physics of gas, stars, and radiation. The visible galaxy is not a passive tracer of the halo. It can reshape its environment, and that makes interpretation harder. Another tension comes from the absence of direct detection. The longer experiments search without finding a dark matter particle, the more pressure falls on the simplest particle models. Weakly interacting massive particles were once attractive, partly because their expected interactions seemed within reach. As detectors have grown more sensitive and still found no confirmed event, many of those simple possibilities have narrowed. This does not disprove dark matter, because the allowed particle landscape remains wide. Axions, lighter particles, hidden sector models, sterile neutrinos, and other candidates can produce weaker or different signals. But non-detection changes the emotional weight of the question. A particle that explains most of the matter in the universe remains physically unidentified. That absence gives alternatives space to continue. It also encourages broader thinking inside the dark matter framework itself. the successful component may not be the simplest cold, collisionless particle. It could have very small self-interactions, or exist in more than one form, or connect to ordinary matter through a mediator too heavy or too weakly coupled for current experiments. These possibilities preserve the central dark matter idea while allowing richer behavior. They must remain constrained by cluster collisions, halo shapes, the cosmic microwave background, and structure formation. The freedom is real, but it is not unlimited. A theory of dark matter cannot be adjusted without consequence. Every new property leaves some trace, even if faint, and those traces can be searched for. The same is true for modified gravity. A change in gravity cannot apply only where it is convenient. It must preserve the precise success of general relativity in the solar system. Binary pulsars, gravitational wave observations, and many other tested regimes, while also changing the behavior of galaxies and cosmic structure. It must explain lensing because light follows space-time geometry, not merely the motion of stars. It must reproduce the early universe because the cosmic microwave background is a detailed record, not a loose sketch. These demands are severe. They do not make alternative gravity unscientific. They make it difficult in the way any broad replacement must be difficult. The leading position of dark matter comes from its ability to satisfy more of these demands at once. Yet the existence of tensions is valuable because it prevents the framework from becoming complacent. The strongest view is neither blind confidence nor easy dismissal. Dark matter is the best current explanation across the widest evidence, but its identity is still missing. Modified gravity and related alternatives have not replaced it across the full range of observations, but they highlight patterns that dark matter must explain more deeply. The unresolved state of the field is therefore not a simple contest between certainty and doubt. It is a layered problem, on large cosmic scales. Unseen mass fits the evidence with remarkable power. On galactic scales, the relation between visible matter and gravitational behavior is more orderly than a careless halo picture might suggest. In laboratories, the dark particle has not yet appeared. In theory, both new matter and new gravity remain difficult to connect fully with known physics. The tension has a shape, and that shape is productive. It keeps experiments broad, simulations careful, and interpretations restrained. For now, dark matter remains the leading framework not because every detail is settled, but because no alternative has matched its combined reach from the early universe to galaxy clusters to lensing and structure. What remains is not a collapse of the idea, but a demand for completion. The universe behaves as though a major unseen component is present, while the deepest nature of that component still refuses identification. That is the point where the final questions gather. Not only whether dark matter exists, but what it is, how it began, how it is distributed, and why it belongs so quietly to the larger laws of the cosmos. What remains unknown about dark matter is not a small detail attached to an otherwise complete picture. It is the central physical identity of one of the main components of the universe. The evidence says that something with mass shapes galaxies, clusters, lensing, and cosmic structure. The evidence also says that this component does not behave like ordinary atomic matter. Beyond that, the deeper description is still open. The first unresolved question is what dark matter is made of. It may be a particle, a field, a population of compact objects, or a more complex dark sector with more than one ingredient. The leading possibilities each solve part of the problem while leaving their own difficulties. Heavy, weakly interacting particles are constrained by direct searches. Axions remain plausible, but require sensitive scanning across unknown masses. Sterile neutrinos must fit both structure formation and possible decay limits. Primordial black holes are restricted by lensing, cosmic backgrounds, stellar dynamics, and other gravitational tests. More elaborate hidden sector models widen the possibilities, but they also introduce new properties that observations can constrain. The unknown is therefore not empty, it has boundaries. Dark matter cannot interact strongly with light. It cannot mostly be ordinary baryonic matter. It cannot move so quickly in the early universe that small structures are erased. It cannot collide with itself too often without changing the shapes and behavior of halos in ways that would already be seen. These limits give science a partial description, but not yet a name, a mass, a charge structure, or a confirmed interaction. The second question is how dark matter began. If it is a particle, it must have been produced in the early universe through some physical process. It may have once been in thermal contact with ordinary matter, meaning that frequent interactions kept it in a shared temperature history before it later separated. Or it may have been produced more indirectly, never reaching ordinary thermal balance. Axions could arise through field behavior as the early universe cooled. Sterile neutrinos could be generated through mixing with ordinary neutrinos or through other mechanisms. Primordial black holes, if they contribute at all, would require early density variations large enough to collapse into black holes before stars existed. Each origin story leaves consequences. It affects the expected abundance, speed, distribution, and possible signals. A successful theory must explain not only why dark matter exists now, but why it exists in the measured amount. That amount is not arbitrary. Cosmological observations show a consistent ratio between ordinary matter, dark matter, radiation, and dark energy in the present universe. Any candidate must arrive at the correct cosmic density without disrupting the early formation of light elements. The pattern of the cosmic microwave background, or the growth of galaxies. This makes the origin problem as important as the identity problem. A particle that could exist but would be produced in the wrong amount cannot be the full answer without an additional mechanism. A mechanism that produces the right amount but predicts detectable signals already ruled out also fails. Dark matter has to fit the full history of the universe, not only the motions of galaxies today. The third question concerns its distribution in detail. On large scales, dark matter models work very well. They explain why matter forms a web of clusters, filaments, and empty regions, and why galaxies appear inside halos. On smaller scales, the situation is more complicated. The centers of dwarf galaxies, the number of small satellite galaxies, and the relation between visible matter and inferred dark matter continue to test the standard picture. These problems may be solved by the messy behavior of ordinary matter, gas inflow, star formation. Repeated bursts of energy and outflows can change the central mass distribution of a galaxy. Small galaxies are also difficult to observe completely because faint satellites can be missed, and their histories may differ from one environment to another, but the details still matter. If dark matter is perfectly cold and collisionless, simulations predict certain halo structures. If dark matter is slightly warm, self-interacting, or wave-like, it may produce different structures at small scales. Observations of faint galaxies, stellar streams, gravitational lensing by small halos, and the motions of stars in dwarf systems can help distinguish these possibilities. The problem is that ordinary matter often complicates the same systems where the differences are most important. Dark matter leaves its clearest large-scale signature where gravity dominates cleanly, but its particle properties may reveal themselves in small systems where baryonic physics is difficult. This makes the next stage of evidence delicate. It requires both better observations and more realistic simulations. Another unknown is whether dark matter has any interaction with itself beyond gravity. The simplest model treats dark matter as collisionless, meaning that particles pass through one another almost always without scattering. This fits many observations, especially large-scale structure and cluster behavior, yet small self-interactions remain possible. If dark matter particles occasionally scatter from one another, they could change the density of halo centers or alter the behavior of merging clusters. Observations place strong limits, but not all self-interaction is excluded. The question is important because it would change dark matter from a single quiet mass component into a substance with its own internal physics. It might still remain invisible to light while behaving in a richer way among its own particles. Such a discovery would open a new sector of nature, one mostly hidden from ordinary matter but active through its own rules. The same possibility applies to multiple dark components. Ordinary matter contains many particles and forces. There is no guarantee that dark matter must be one simple particle. It could be that the dark side of the universe is simple, but simplicity has not been proven. At the same time, added complexity must earn its place. A complicated dark sector cannot be accepted only because it is possible. It must explain observations better than the simpler model and avoid producing signals that should already have been detected. Dark matter also remains connected to the larger question of gravity. The success of the dark matter framework does not eliminate the need to keep testing the law of gravity across scales. General relativity is extremely successful, but galaxies and cosmology probe regimes very different from laboratory experiments in the solar system. Modified gravity ideas have not replaced dark matter across the full range of evidence, yet they highlight real regularities in galaxy behavior. The close relation between visible matter and observed acceleration in many galaxies remains an important clue. It may emerge naturally from the way galaxies form inside dark matter halos. After ordinary matter cools, forms stars, and reshapes the gravitational field. Or it may point toward deeper physics not yet understood. The question is not simply whether gravity or dark matter is correct in a simple opposition. A more complete theory may explain why the dark matter distribution and ordinary matter distribution become so closely linked in galaxies while remaining clearly separated in some cluster collisions. It may preserve dark matter as a substance and still revise parts of the theory around it. The final unknown is why dark matter has remained so hidden. If it is abundant enough to outweigh ordinary matter, its silence is striking. It shapes visible structure but has not entered the laboratory as a confirmed event. It bends light but does not shine. It holds galaxies in larger halos but does not form atoms, planets, or chemistry as ordinary matter does. That does not make it impossible. It shows that human instruments are searching for a kind of contact that may be extremely rare. The next confirmed signal could come from an underground recoil, a narrow axion conversion line, an unexpected collider imbalance, a precise astronomical feature, or a pattern in small-scale structure that no ordinary process can reproduce. It may also come from a combination of clues rather than one dramatic detection. A particle discovery would be strongest if it connected laboratory physics with cosmic abundance and astronomical behavior. Until then, dark matter remains both a major success and a major absence. It is successful because it organizes many independent observations into one coherent framework. It is absent because the physical substance has not been isolated. That combination is what gives the subject its lasting importance. The universe appears to have a hidden mass component that helped build the visible cosmic order, yet the component itself remains outside direct identification. The unanswered mass is not a failure of science to look carefully. It is a sign that the universe can be understood in layers. Gravity has revealed one layer with unusual clarity. Particle identity has not yet followed. The remaining work is to bring those layers together so that the mass known through galaxies, clusters, lensing, and the early universe can finally be connected to a specific form of matter or to a deeper revision of the laws that describe matter and gravity together. Dark matter leaves the story in a quiet, unfinished state. It is not seen in the way stars are seen, and it is not held in the way ordinary matter can be held. Yet its influence remains written through the universe with unusual consistency. Galaxies rotate within wider mass structures than their light reveals. Clusters hold together under gravity stronger than their visible contents can supply. Distant light bends around mass that does not announce itself by shining. The early universe grows into structure more naturally when this unseen component is included. Across these different lines of evidence, dark matter becomes less like a single mystery placed at the edge of astronomy, and more like a hidden condition beneath much of cosmic history. Still, the deepest question remains open. A name has been given to the gravitational pattern, but the substance behind that pattern has not yet been identified. It may be a particle waiting below the reach of present detectors. It may be a field with signals too faint to isolate so far. It may belong to a larger dark sector, mostly separate from ordinary matter, or it may reveal that the connection between matter and gravity has a deeper form than current models describe. Science moves carefully because each possibility must answer to the same evidence. It must fit galaxies, clusters, lensing, early light, and the growth of the cosmic web. That is why the question endures without becoming vague. The unknown has boundaries, and those boundaries are slowly being pressed inward. For now, dark matter remains one of the calmest and most persistent reminders that the visible universe is not the whole physical universe. Much of what gives structure its shape may remain unseen, present not through brightness, but through the gravity it leaves behind,